it's going to be Rick Hall talking on continuous convergence in R of L. And it is my pleasure, of course, to invite you to speak, Rick.
Thank you very much. I'd like to extend my heartfelt thanks to the organizers. Always benefited from get-togethers like this. And I have a particular connection to this conference because it was 13 years ago when the conference was organized by my good friend Nick Galatos and Natasha Dobrinin at the University of Denver. So to all of those, I extend my hearty thanks. And my collaborator, one of them, is also here. So the thanks go all around. My topic is quite classical in origin because it involves the famous duality between spaces and either L groups or Banach algebras or C-star algebras. In any case, in the one side of the adjunction, there is a algebraic object, and on the other side of the adjunction, there's a geometric object. In this case, the specific form that that adjunction will take is called the Yoshida adjunction, and I will start with not the early history, but the point-free version, which is due to Madden and Vermeer. The category on the algebra side is W. That's our symbol for Archimedean vector lattices with a designated weak unit. And the category on the other side, the geometric side, is the category of point-free spaces, which I will refer to as frames. Everything in this talk is assumed to be completely regular, okay? The duality goes as all dualities go, that is to say the adjunction. If you give me a W object G, then associated with it is a unique frame L and a W isomorphism from G into R of L. Now, R of L is the W object of frame maps from the topology of the real numbers into L. That's the point-free version of C of X. And that arrow is universal among all such arrows in the usual sense. It is any other W homomorphism from G into some randomly chosen R of M is realized by a frame map little m, which explains theta by composition with the representation. Right? The frame is called the Madden frame in honor of its creator, and it consists of the W kernels of the W object, and therefore I will use K of G to designate it. Okay? So again, pictorially, we have this connection between the world of geometry, those being frames, and the world of algebra, those being the W objects. And the translations are the R functor and the K functor that I've mentioned. The objects fixed by the adjunction are always of interest. It turns out that on the left, if you start with an arbitrary frame, pass to its R of L, and then extract from it its Madden frame, you are not necessarily back to where you started. You instead are always going to have a Lindelof result because it happens that the W kernel frame is always Lindelof. So the fixed objects in that side of the adjunction are the Lindelof frames. And on the right side of the adjunctions, they constitute a rather mysterious class, which I have designated R of L. So these are the R of L's for some L. An interesting feature of this setup is that one has in frames something called the Lindelof co-reflection. It's the Lindelof version of the check-stone compactification. But the novelty here is that one does not have this in spaces, right? It's one of the more attractive features of frames. But what it means here is that any frame map from O of R, which after all is Lindelof, into this random frame L, lifts to the co-reflection, right? And therefore, R of L is the same as R of the co-reflection. So that means that R of L does not see L very clearly at all. you see? And I think that for my purpose, in fact, I know for my purposes, that's unfortunate. And I will speak to that issue in this talk, which is to say, I hope to redress this grievance. Characterizing these objects which are fixed on the algebra side is tricky. Even in the classical setting, the characterization of C of X is not easy. In fact, my collaborator, Tony Hager, has written several deep papers on this subject. Most interesting results are negative, right? C of X cannot be characterized in any one of the ways that would occur to you on a first pass, right? R of L objects are also tricky. Tony and I have written several papers on that topic, and I will have more to say about that a little bit later. However, significant is the fact that the characterization that I will come up with at the end of the talk involves a convergence, right? Now, this is perhaps not surprising when you think back to the original Yoshida adjunction, because there, the algebraic objects which are fixed are the uniformly complete strong unit W objects. And that, of course, is a condition having to do with a convergence, namely uniform convergence. So we are on firm ground historically here. So what do I mean by a convergence? Well, convergence on a set is simply a decision as to which filters converge to which points. The only conventions are extraordinarily mild. You want the principal ultrafilter of any element to converge to it. You want any filter which is finer than a convergent filter to also converge. And if two filters converge to the same point, then so should their intersection. The intersection of filters being generated by the set you get by taking the union of the base sets for either of the filters in the intersection. It's said to be Hausdorff if any filter can converge to at most one point. Okay? Think of these filters as being stand-ins for the neighborhood filter in a topology. Right? It's just that you may not have a topology in the background. If the object underlying this convergence is, in addition, a W object, then you want to insist that the operations of W be continuous with respect to this in a more or less obvious fashion. That is to say, for any of the L group operations, doing those operations on the base sets, thereby generating the corresponding operation on the filters, should be continuous, right? Continuous in the sense of convergence. I'm going to call it a W convergence if it has an additional feature, and that is that by convexifying the base sets, I get a convergent filter to the same point, right? So this simply avoids some of the pathologies that can arise in an ordered context. This, however, is a more interesting requirement. E of G is my symbol for, well, let me say it this way. In this context, it's reasonable to wish that the sequence G over N should go to 0 as N approaches infinity, right? Why? Well, that's precisely the requirement of Archimedeanness, right? And therefore, certainly we want that. And we're going to build it into the convergence here by defining E of G to be the corresponding filter. That is, that's the filter which corresponds to the sequence G over N. And so as a matter of fiat, I am asking that that be part of the definition of what I'm calling a W convergence here, okay? It, by the way, implies the Hausdorff property. So all W convergences will be Hausdorff. What's interesting here is that, as is the case in topological groups, one of these W convergences is entirely determined by the filters which converge to 0, right? In the following sense, if you look at the family of such filters, it should, of course, contain all these E of Gs. And it should, of course, be closed under taking bigger filters. And finally, if it contains a filter, right, meaning that that filter converges to zero, then so should the negative of the filter and twice the filter and the convexification of the filter and the intersection of two filters, right? So all of these are simply reiterating the requirements of continuity, right? But the converse is not correct. So if you then give me a set of filters of this type, I can then recreate the convergence by the simple stratagem of defining F convergent to G precisely when the difference filter F minus G dot is in the W, right? So again, what this means is that for all purposes dealing with these convergences, you can focus only on the filters convergent to zero. So I get dizzy when I think about this unless I sit down and draw a very careful set of poset, and here's my attempt to do that. So this is a picture of W as a subset of the poset of all filters, right? So up top, you've got the ultrafilters, right? And some of those are principal, most of them are not, okay? The W, however, contains only one of the non-principal ultrafilters, namely 0, if it's to be Hausdorff. So the Hausdorff axiom says that the only principal ultrafilter that's in the W is the 0. You see, if you pull that dotted line down too far, you'll pick up more, and that would then destroy the Hausdorff property. So this is a limitation on the size of the W. And then, of course, the very smallest trivial filter is at the bottom of the picture. So there are numerous examples of things. There's actually quite a bit of literature on it. I might point out that classical uniform convergence is the convergence generated by the single filter E of 1. Right? So this is quite close to home. That we will give a name to the smallest W convergence. That's the convergence which contains only the E of G's. I will call that Archimedean convergence. One of the convergences which has a robust representation in the literature is order convergence. Here you decree that a filter will converge to 0 if, let's see how best to put this. If you look at the set of upper bounds for one of the sets in the filter, right? Those are the little g's. And here I mean an upper bound in the L group. Then that should give you a filter which meets to 0 in the L group, right? So that's saying that these F's get slimmer and slimmer, closer and closer to 0, right? That's one of the interesting things here is that this gives you a Cauchy completion, which is the classical Dedekind-McNeil completion of the L group. That's the biggest L group in which the starting L group is both join and meet dense, right? Very classical stuff here. Fred Dashiell and Tony Hager and Mel Henriksen wrote a beautiful paper in which they pointed out that the omega version of order convergence gives as its Cauchy completion the, well, if you start with C of X, X being compact Hausdorff space, the Cauchy completion gives you C of the quasi-F cover, which is a beautiful result, right? This tells you precisely how the elements of the quasi-F cover of a compact Hausdorff space are approximated by the functions on the space itself. Here's an important one for our purposes, and it's the picture on the left. I hope the people viewing this remotely can see the picture on the left. This is called alpha convergence, and it has been investigated at some length by myself and Gary Davis. Convergence to 0 here says that for every positive element in the W object, that's the G, you can find a second element strictly less than the first, but still positive, such that everything in the W object which pushes the larger one down below the smaller one, that's a subset of the W object, which must be present in the filter. Okay, That's the definition of this kind of convergence. So think of this as kind of a bubble, if you wish. And what it says is all the gadgets which depress the bubble have to be a set in the filter, right? And if for every possible challenge, every G, you can find a bubble of this kind, that's a filter which converges in this alpha sense. Okay. I then have to impose a technical requirement, which in the interest of time I will suppress. But it gives me now, it leads me to the category enriched by these convergences. So I'm calling this the CW category. The objects are of the form of a W object paired with a specific convergence. And the homomorphisms are simply the W homomorphisms, which are continuous with respect to the convergences. And when you simply look at this carefully, you see that every W homomorphism is continuous with respect to the smallest of these convergences, this being the Archimedean convergence. You can also show that the complete W homomorphisms, the ones which preserve all joins, are also continuous with respect to the coarsest of these convergences. But now, my goodness, now I have to tell you about going the other way through the adjunction. Once you have one of these CW objects, you have a natural closure operator on the frame of W kernels, right? Namely, the passage from any W kernel to its X closure, its convergence closure. And that, one can readily see, is a nucleus on this frame. And therefore, its fixed points, that is the set of X closed W kernels, constitute a sublocale and therefore a frame in the inherited order. And I'm going to call that frame K sub C of G, right? So those are the convergence closed W kernels. And I'm going to call the corresponding nucleus Q sub G, okay? And then, as it happens, this turns out to be a functor. That is to say, it not only gives you an object, but it also gives you a map. And the reason is that here, this little diagram, if you take a continuous W homomorphism from G to H and apply the adjunction, the classical adjunction without the convergences, then that frame map going from KG to KH drops through the nuclei and therefore gives you a continuous frame map on the convergence closed kernels. So all that is to say that we have a functor in one direction between the category frames on the left and the category of convergence W objects on the right. I'm pushing my time, and so I'm going to be a little less loquacious in the next few slides. This raises the key question here, and that is, could it possibly be that we have a functor in the other direction? I think it's audacious to expect that we might, simply because you're asking for a single canonical W convergence, right? One which functions in a universal fashion. And it was a considerable surprise to me to learn that the answer is positive. Not only that, but it's quite familiar. This is the frame version of classical continuous convergence, right? It has a beautiful frame formulation, and you see it there, right? A filter is going to converge to zero precisely when this particular calculation gives you the top element of the frame for every possible epsilon. The symbol there is the image under a frame homomorphism of the epsilon neighborhood of zero. That's the 0 to the epsilon. And the condition is that for a particular set in the filter, you want to look at the image of the epsilon neighborhood of zero, the meat of the images of that open set under all of the members of that set, all of the Roman Fs, and you want then to range over the filter in such a way that that frame element eventually climbs up to the top. Okay. And then it turns out that this is one of the types of W convergence that we are interested in. And here is something that I really find surprising to this moment. It turns out that with respect to this convergence, R of L is complete. Every C Cauchy filter in R of L converges. Not only that, but for every sub-object of R of L, at least big enough so that its co-zeros join generate L, this sub-object is C-dense. So R of L is in fact the Cauchy completion of any reasonable sub-object of R of L with respect to continuous convergence. So this instantaneously means that you can recover the frame details from the convergence on the W object. Furthermore, it turns out that the imposition here is functorial. I will, again, skip and fly here. The point, I guess, is that we do then have a full boogie adjunction when we make this assignment. Just to paint the big picture once more, I forget where, yeah. Now we have an arrow going the other way, right? So to reiterate, the arrow going from right to left is simply the arrow that assigns to every one of these convergence W objects the frame of its convergence closed W kernels, and the arrow going in the opposite direction attaches to any frame whatsoever its R of L with the continuous convergence. Okay? What are the objects fixed by the junction? Well, here we have a very favorable outcome because it turns out that every frame is fixed, right? Every frame is fixed. So it's interesting. If you don't have a convergence, you see, you lose the details of the frame. But even though that's true, by adding the convergence information to the W object, you then are able to see every detail of the frame. And this means this is a favorable development if you're interested in those qualities of the W objects, which are essentially originating in the frame, right? We can now see them by imposing this convergence. I won't say more about that, except to say that what we then have, if we look at the fixed objects, is an equivalence of categories between frames on the left and the complete objects on the right. Completeness here means Cauchy completeness of the W object together with the maximality condition on the convergence, right? It has to essentially be continuous convergence, and then it's a fully equivalent category. Just to bring this home a little bit closer, this means that we can now characterize R of L as follows. You are given a W object, and the question then is this R of L for some frame L? And the answer is, if and only if it is Cauchy complete with respect to the coarsification of Archimedean convergence. Right? Quit there.
Are there any questions?
Is Archimedean convergence the same thing as relatively uniform?
Kissing cousin. Kissing cousin. Very close.
What's the difference?
The difference is you have to coarsen it, but well, first of all, the closure operator of Archimedean convergence just gives you, the closure of every W. The closure of every convex L subgroup under Archimedean convergence is the W kernel. So it's equivalent to relative uniform convergence from the point of view of the closure operator, right? Yeah. This CA is basically, let's see, you take the Archimedean convergence, represent the object inside the God-given Madden frame, and then you coarsen the convergence by actually taking the continuous convergence on that RFL, right? Anyway, the answer is yes, it's very, very close, right? But keep in mind, that's the finest one. So we have then a huge abundance of other convergences. And in fact, what you can show is that every one of the convergences I've done, by the way, this technical requirement applies to every convergence that anyone has ever thought about, right? It's really not a severe restriction. But it turns out that all of these convergences sit between the A convergence, the smallest one, and alpha convergence, the coarsest one. So the entire world that we're talking about lies between those. And this one gives you back the Madden frame, and this one gives you the Booleanization, right? So there's a really nice matchup there between convergences on the one hand and essentially all the L groups that you would like to look at between G and its essential closure.
I have another question.
Well, go ahead.
Just, this one probably has a brief answer. Can this generalize to arc?
Ooh, haven't thought about it, John. Yeah, that's a good question. I don't know.
Any other questions? Are there any Zoom questions, Peter? Nobody's asking. All right, well then let's thank Rick once again.